Hello everyone. What I want to do now is go through an example, and I want to discuss a very general method for proving pointwise and uniform convergence of Fourier series. And by that I mean actually proving the pointwise and uniform convergence of a very typical infinite series that arises when you compute the Fourier coefficients of a very typical practical function. We're not necessarily going to prove using this method that the Fourier series converges to the original function. We're going to have to get to that in a little bit. We're going to start that in the next video. But at least this method we'll discuss will prove for a lot of different Fourier series convergence of the infinite series. Okay, and this is not going to be it's not really a theorem that I'm going to prove. It's just a general method that works quite often in practice. All right, so let's go look at an example. And let's look, this example frankly illustrates the deficiency in the theory that we talked about last time, which is fine because, as I said, these are just very general theoretical results that sometimes in practice are useful, but it's more just a general, it's more just very general results, and it's probably the best general result you can prove. Okay. Okay, so this example is x times 1 minus x, okay? And if we treat this as a periodic function, or rather we extend it periodically to all the real line, we basically get a bunch of mountains here. Of course, f prime is 1 minus 2x, so this has on 0 to 1, it has a maximum at 1/2, which that y value is 1/4. Okay, so thinking of this as a function on 0 to 1, f prime is continuous on 0 to 1. Again, remembering that when we say continuous on 0 to 1, we mean, we're looking, when we say continuity at 0, we're looking, taking limits from the right, and continuity at 1, we're taking limits from the left. Okay. On the other hand, strictly speaking, just as a function on the real line, this periodic extension, the derivative is going to look like this. Okay, but again, 1 minus 2x as a function on 0 to 1 certainly does, it's certainly continuous on 0 to 1. And I have these circles here because really as a periodic function, the left derivative and the right derivatives don't coincide. This is typically what happens. And we'll actually look at what happens to Fourier series at these kinds of jumps. So this is a very typical, function that you would want to, look at from the perspective of Fourier series. It's a nice periodic function that you probably actually found the Fourier series of something like this, if not this, if you've taken a course in partial differential equations or methods of applied mathematics. Okay, so let's get the Fourier coefficients. So certainly this function here, x1 minus x, satisfies the condition of our proposition here when n equals 1. As I mentioned, 1 minus 2x is obviously continuous on 0 to 1. And certainly here when n equals 1, f of 0 is f of 1. L equals 0. The 0 derivative is the function itself. Okay. So we know that the Fourier Fourier coefficient at k is 2 pi I k to the minus 1 times the Fourier coefficient of the derivative. Right? Well, we just got that from integration by parts, if you remember. So instead of actually using this theorem, let's just do the integration by parts. You should check yourself that if you use this theorem and find the Fourier coefficient of 1 minus 2x, which we'll implicitly do, you get the same answer that we get. All right, so just doing the integration by parts, we get the following, right? So of course, your dv is e to the minus 2 pi I kx dx. Your u is x, 1 minus x. So uv, 0 to 1. Integral v du. du is 1 minus 2x dx. This, of course, is 0. Plug in 1, plug in 0, you get 0. So we do another integration by parts here. U is 1 minus 2x, dv e to the minus 2 pi I kx dx. So this definitely is not 0 when you plug in 1 and plug in 0, which is fine. Okay. On the other hand, when k is not equal to 0, which implicitly it's not, I should maybe have mentioned that, but implicitly k is not equal to 0. This integral, when k is not equal to 0, we did this at least twice already. It's going to be 0. So this whole thing is just going to be whatever this is. Plug in 1, you just get minus 1 on top. 1 minus 2 is minus 1. Plug in 0. Or rather, let's, so we plug in 1 and plug in 0, we get a common minus 1 in this numerator here. So rather, let me get the pen out. It's over. Right, so we plug in 1, plug in 0, doesn't matter. This whole thing that I'm circling is going to be minus 1. Right, so factor out that minus 1. 1 minus 2x is minus 1. 1 minus 2 times 0. Sorry, 1 minus 2 times 1 is minus 1. And then 1 minus 0 is 1. So it's minus 1, minus 1. And this just becomes minus 1 over 2 pi squared k squared. Okay. Now it's might be a little curious that, hey, wait a minute, there's no imaginary stuff here. But we're going to have complex exponentials floating all over the place. And obviously, x1 minus x is real. All right. So let's do a sanity check if you haven't done Fourier series before. And let's actually check that we do get everything real. Okay. And of course, I should mention that f hat of 0 is just, well, when k equals 0, the exponential goes away, and this integral is just trivially 1 over 6. So the Fourier series is as follows, and this is typically what you do when you actually compute Fourier series. You basically have k equal, you start off with the 0 term, the constant. Then it's k equals 1, k equals minus 1, k equals 2, k equals minus 2, and you group those together. Okay. So in particular, you'll notice that the Fourier coefficients are the same whether we have k or minus k. And of course, the only difference with the complex exponential is for, this one, of course, that I'm circling is going to be k equals 1. Right. And there's no different for k equals minus 1, nothing different except, of course, it's going to be e to the 2 pi I minus kx, which is e to the minus 2 pi I x. All right. So this one here would be k equals minus 1. All right. And it's the same kind of thing for k equals 2 and minus 2, etc., etc. Okay. So when k equals 2, it's 1 over 2 pi squared times 4, which is 1 over 8 pi squared with, minus. Right? All right, and you'll notice that when you do this pairing, as the sanity check works, nothing crazy going on. This is just going to be, this whole thing here is 2 cosine 2 pi ix. This is 2 cosine 4 pi x. I think I said pi ix. Sorry, I meant this whole thing here that I'm circling is cosine 2 cosine 2 pi x. This whole thing here is 2 cosine 4 pi x. And you get the same pattern. Basically, keep going, you'll get the following here. Okay. Now, you'll notice something really curious, and I don't really want to spend too much time on this, but if you play around with Fourier series, you can come up with all kinds of funky sums that when you plug in x equals 0, assuming that, so actually I shouldn't really say f of x equals. We don't know if f of x equals this yet, and we don't know in what way, shape, form, but really I should say here that the Fourier series is going to equal this here. Now, assuming the Fourier series, assuming f of x is going to be this whole thing, particularly at the very least for x equals 0, you'll plug in x equals 0, you get 0 equals 1 over 6 minus 1 over pi squared sum 1 over k squared for k equals 1 to infinity. That's really curious. That tells us that the sum of the inverse of the squares is pi squared over 6, right? Yeah, so like I said, I mean, if you play around with similar functions, you can get some of the 1 over the cubes, 1 over k to the 4th, et cetera, to come up with all kinds of funky summations. And actually, you know, in the next lecture or two, we will prove that at least for x away from the integers, that f of x is actually given by its Fourier series. And by f of x, I mean, well, actually, in this case, for all x, we will actually get that f of x will coincide pointwise with its Fourier series, which is computed, where f of x is this kind of series of mountains here. Okay. All right. Right. So 2 kind of notes. One is that if we actually go back, as I said, use this proposition here, kind of use it backwards, we would get that the Fourier coefficient of the derivative is 2 pi I k times the Fourier coefficient of k, and just plug and chug. We actually, you know, we just computed this. So this becomes I minus I over pi k. And that's not very good. That's certainly not enough decay to invoke this corollary. Okay. All right. And right. Yeah, I should say this is when k is not equal 0. The you know, when k equals 0, the Fourier coefficient of the derivative is 0. But anyway, so yeah, this is not enough decay for this sum to converge when n equals 1, because this sum is going to be like, you know, it's going to be, you know, it's going to be basically, it'll be basically k equals 1 to infinity, 1 over k, and we know that diverges, that blows up to infinity. On the other hand, yeah, and I should mention, this is definitely still true for both f and f prime, because both are L1. So, you know, in this example, we have decay like 1 over k squared, decay like 1 over k for f and the derivative, respectively. Okay. On the other hand, we can use this corollary because the proposition works when n equals 1. Okay, so you can use this corollary that I'm just was up a second ago to conclude that the Fourier series for 1 minus 2x is just the same thing as if you term-wise differentiate the Fourier series we just computed, or we've implicitly, if you really go back, we did the integration by parts for 1 minus 2x e to the e to the minus 2 pi I kx. And if you do that and do the same kind of game that we did here, you know, combining the terms k equals 1, k equals minus 1, k equals 2, k equals minus 2, et cetera, et cetera. If you do that, then you'll get that the Fourier series for 1 minus 2x is 2 over pi times this sum here, right? Now, you'll notice that for this Fourier series here, we know by the Weierstrass M test that this is going to converge uniformly for all x. Right? On the other hand, we cannot use a Weierstrass M test here to conclude anything about convergence, because you smash in absolute values, then all we can say is that this is going to be dominated by some k equals 1 to infinity 1 over k, and that most definitely does not converge. Okay, so we need something, you know, to study Fourier series like this, where we have, you know, a sine term like this, and we have some decay, not enough for Weierstrass M test, but we still have decay. We need something a little more subtle. And I should say this is typical of a lot of Fourier series. You know, you have a sine or cosine like this, 2 pi kx or something like that. And then you have like a k in the bottom, something like that. Very typical. Okay, so how do we prove convergence of something like this? Well, there's something called the Dirichlet series test. And let's describe that. Okay. So first we need something called summation by parts, which if you've taken a analytic number theory, or, you know, in general, like a number theory course anywhere, like a more advanced number theory course, you might have seen this before, maybe in slightly different formulation. Yeah, definitely a very useful tool in analytic number theory. So it's really a discrete math lemma, and it looks very strange, but it's extremely useful for us, as we'll see in a moment. So what is summation by parts? If Sn is the partial sum of AK, and if n is bigger or equal to 2, then I claim that this finite sum here, so no issue of convergence here, this finite sum is given by this weird-looking sum here. Okay. So let me just prove this. I was thinking about giving this as a homework, but I'll just prove it. Okay, so it's a pretty easy induction, really. So let's start off with n equals 2. So a lot of people state this for n bigger or equal to 1, which this kind of sum here doesn't exactly make a whole lot of sense when n equals 1. I don't know how you sum up from k equals 1 to 0. So, yeah, anyway. All right, so n equals 2. Let's just check. Both sides are equal. Not much to this, really. So let's work with the right-hand side. First, when n equals 1, k goes from 1 to 1, so there's only one term. So it's just S1 B1 minus B1 plus 1 is B2. N equals 2, so it's S2 B2. All right, well, S1 is just A1. S2 is A1 plus A2, just by definition of Sn. So plug that in, A1 B1 minus B2 plus A1 plus A2 times B2. And you'll notice, of course, that these two cancel out, that I am putting in. Now these two cancel out here, A1 minus B2, A1 B2. So we're left with A1 B1, A2 B2. We're left with these two here, right? Then I'm putting in a square. Okay, and that's exactly what we're trying to prove when when n equals 2. It's a1, b1, a2, b2. Okay, and now just do an easy induction. Assume it's true for n. So you kind of do the obvious thing. You write the sum k equals 1 to n plus 1. It's k equals 1 to n. an plus 1, bn plus 1. You dump in your inductive hypothesis. And the an plus 1, bn plus 1 just comes along for the ride. And you hope all is well. Right? And all will be well. Okay, so what I'm going to do is I'm really going to add and subtract Sn times minus Bn plus 1. So here it's a minus, and here it is a plus. Okay. So yeah, so I'm just subtracting. So it's minus Sn Bn plus 1 plus Sn Bn plus 1. Otherwise, it's the same sum here, and then Sn Bn, which I'm putting in a box here. And this is already in the box. So an plus 1, bn plus 1, an plus 1, bn plus 1. Okay, so what's the purpose of this? Well, what I can further do is, the purpose is, I get the next term. Well, I get basically the next term in this sum here, and that's right here. So I basically combine all this into one sum that I'm putting in a rectangle. That's just k equals 1 to n sk bk minus bk plus 1, right? And what I could do also is factor out a bn plus 1 in these two here. So it's bn plus 1, an plus 1 plus sn. But what is sn? Let's go back. Sn is k equals 1 to n, ak. So you add an plus 1 to sn, you get sn plus 1. Okay. And that proves it for n plus 1. Right? This that I have here circled is exactly the same thing as this here, except rather it's exactly the same thing as this here, except except instead of n, it's n plus 1. K equals 1 to n, Sn plus 1, Bn plus 1. Right? And that completes the proof. So it's a, I probably could have given as a difficult 299 problem, but basically discrete math problem. All right, so what is the Dirichlet test? The Dirichlet test is a very general infinite series test. You can theoretically state it where the BKs are allowed to be functions, but in practice, we really want the BKs to be just a sequence of real numbers that's monotonic and converge to 0. So particularly, we're thinking like BK is 1 over K, or BK is minus 1 to the K over K. Sorry, that wouldn't work exactly. But anyway, so let's say we have a sequence of functions. Certainly BK is 1 over K would work. Or BK is just minus 1 over K would work, something like that. Let's say we have a sequence of functions, AK, where the sum is bounded above an absolute value. Not when you smash in absolute values, but outside of the sum. And this is for all x in some set A and all natural numbers n. Then the claim is that I have uniform convergence on A. Right? And the proof is relatively straightforward using summation by parts. So what I'm going to do is basically just use the Cauchy criteria for uniform convergence. So let epsilon be bigger than 0. I'm going to find a big N, where if N and M are bigger than big N, and without loss of generality, assume little n is bigger than big M, where this implies that the uniform norm, the sup norm of this here is less than epsilon. If this is true, then the partial sums are Cauchy in the sup norm over A, and hence are uniformly convergent to something. Okay, so what do? I just plop in the summation by parts formula. So let's fix some x in A. All of my estimates are going to be independent of x, and hence take the supremum, and everything will be fine. All right, so I just plop in summation by parts formula for n. So here sk is going to be, well, k equals 1 to n of ak. All right, so this is my summation by parts formula, for this one. And do the same thing here. Just plop in the formula for summation by parts here, except instead of n, it's m. Again, Sm is the sum k equals 1 to m of ak. All right. Well, of course, there's cancellation here. And this just becomes very trivially k equals m to n minus 1, sk of x bk minus bk plus 1. And we still have the Sn of x bn. And we still have the Sm of x bm. They don't go anywhere. They're still there. Okay. But it's just fairly trivially, the terms k equals 1 to m minus 1 are all the same terms that are here. They all get canceled out because n is bigger than m, because these sums are basically the same, except we, continue on farther than we do here for this sum with n versus the sum with m. Okay, so all these terms cancel out. K equals 1 to m minus 1. Now we're in a position where we just smash in absolute values. The hard work, essentially, and the subtlety was the the summation by parts formula. Okay. So now we smash in absolute values, and this is the beauty and utility of summation by parts. We have an estimate on sk of x. This is, it's not sk of x. Maybe this is unfortunate notation, but using k. But anyway, this here is Sn of x. And I know for any x whatsoever, that's my assumption, absolute value of Sn of x is bounded by big M for some positive big M. And that big M is completely and utterly independent of n, right? So we know this thing here is less than or equal to m. This is less than or equal to m. And this also is less than or equal to m. Okay. Now let's, without loss of generality, assume the BKs are increasing. If the BKs are decreasing, instead of BK minus BK, or let's just assume that they're increasing. Okay, so plop in M's everywhere. And because we're assuming this is increasing, this right here is going to be equal to this right here. Absolute value of bk minus bk plus 1 is equal to bk plus 1 minus bk. If the bk's were decreasing, then it would stay bk minus bk plus 1. Okay. All right, so should be a bracket here. So now this is a telescoping series, telescoping finite series. Okay. And everything cancels except the first and last term. So this is m, bn minus bm, big M, absolute value of bn plus absolute value of b little m. Now, certainly, bn is less than or equal to its absolute value, and minus bm is less than or equal to its absolute value. So you just get 2 big M times absolute value of bn plus absolute value of bm. And we're basically done. We can make this less than epsilon absolutely trivially by picking big N where m bigger than n, and thus n bigger than n, implies that big M and big N is less than epsilon over 4m. Here we're assuming this big M is bigger than 0 rather. But we're absolutely allowed to do this because that's our assumption. We're assuming, let's get rid of all this. Sorry about that. We're assuming that the BKs converge to 0 as k goes to infinity. Okay? So it's a really beautiful application of summation by parts. Okay. Okay. Right, and that proves it. Everything was independent of x completely. So the supremum of this whole thing here over x and a is less than epsilon, where big N is picked, where this is true. Okay. Right, and that proves uniform convergence. Okay. All right, so let's start putting this to use. So we're going to need the following lemma, and this is going to be for homework that I'll collect. Basically, it's really doing this problem here, proving this lemma is a question of, did you watch the video where I derived the Dirichlet kernel formula? You're going to basically do something very similar here. You can actually prove this lemma using, I think, the addition formula for sine and cosine. I think the complex, using complex exponentials and geometric, finite geometric sum is a little nicer. But anyway, so right, so yeah, the sum k equals 0, which is really the same as k equals 1, because when k equals 0, sine 0 is 0. The sum here just becomes sine pi nx, sine n minus 1 pi x over sine pi x. Basically the same thing, except we have cosine here versus a sine here. So same thing, sorry, when instead of sine, we have cosine. Okay. So now we have everything we need to study your typical series that comes out of practical computations for Fourier series and Fourier coefficients. And we'll just illustrate it by looking at exactly what we had before, the Fourier series for 1 minus 2x on 0 to 1. So the claim is that this pointwise converges on the real line, and it converges uniformly over any subset of the reals that is away from the integers. By that, I mean that the distance between a and the integers, which by definition is the infimum of all these distances between x and a and natural numbers n, is strictly bigger than 0. So it converges uniformly, essentially, away from the integers, or more carefully, as long as we're strictly away from the integers by a actual non-zero amount. Okay. we will actually prove that we do not have uniform convergence on all the real line. And actually, we have, we do not have uniform convergence over any interval 0 to a, no matter how small but positive a is. Okay, well, anyway, so the proof is very easy. The hard work is already done. Let's say bk is 1 over k, and ak is sine 2 pi kx. We're going to invoke the Dirichlet series test. So it's not surprising that Dirichlet, who studied Fourier series and came up with a very useful general convergence theorem for when a function equals its Fourier series, came up with an infinite series test that's basically tailor-made to study convergence properties of series that pop up from Fourier series. Okay, so really, this is just tailor-made for Fourier series, this Dirichlet infinite series test. All right, so obviously bk is decreasing, obviously converges to 0 as k goes to 0. So one of the nice things is even if you get something like square root of 1 over square root of k, or something way worse than, you could even get like 1 over natural log of k. It doesn't matter how it decays, as long as it converges to 0 as k goes to infinity, we're good to go. All right. So this sum here, just plug into our formula. Instead of n minus 1, we have n here. All right. And the top is just bounded above by 1. Absolute value of sine anything is less than or equal to 1, as long as we plug in real values. Okay. Now, on the other hand, the denominator, since x is away from the integers by a fixed amount, a non-zero amount, we can say that the denominator does not, 1 over the denominator does not blow up to infinity because the denominator is away from 0. The only way sine pi x is going to be 0 is if x is a positive or negative integer. Right? So this whole thing is bounded by a bound depending on a, right, and that's because, whatever x is, absolute value of x minus any integer is bigger or equal to this positive number here, whatever it is. So, right. And of course, as we kind of approach, as x approaches an integer, this definitely will possibly blow up to infinity, this 1 over sine pi x, so we really can't necessarily bound this, which is fine because I said we do not have uniform convergence on all the real line. Right? We, in fact, don't have uniform convergence on the closed interval 0 to a for any little positive number a. Okay? So nothing strange going on here. So yeah, we're done. The Dirichlet test concludes immediately that we have uniform convergence. All right. Well, what about convergence? So this clearly proves pointwise convergence on the real numbers take away the integers. Obviously, you can just, for any x, you can just take a little interval that's away from the integers by some fixed positive amount. Well, what about the integers? Well, there's nothing subtle going on when you plug in an integer. Sine pi km for any m, that's an integer. And any k that's a positive integer is trivially 0, because this whole thing for any m is just 0. Right. So not a whole lot of subtlety here. Okay. And I should mention that this is exactly what typically happens. We'll see this in the next 2 videos, or maybe 3 videos, but this is this is what exactly should happen when we have jumps like this. We can exactly say what happens to Fourier series when we have these kind of jumps. I don't want to give a spoiler, but you can kind of maybe even guess what might happen at jumps based on the fact that the Fourier series is 0 at all of these jumps. For this example, the jumps occur at integers m. Anyway. Okay, so finally, let's end this by proving non-uniform convergence. Okay. So let's give this function a name. We know this infinite series exists. That should be 2 pi ikx. This is a little messy here. We know this infinite series converges for all x. So let's give it a name, call it big F of x. Let's say big Fn of x is just k equals 1 to n of these here. So I claim, as I said, that we do not have uniform convergence on any of these intervals for any positive a, no matter how small a is. And this is not terribly subtle, really. Let's just see what's going on. There's a million different choices for xn you can pick. The idea is that we're going to pick essentially a sequence converging to 0 where fn of xn is bounded from below away from 0. That'll miserably screw things up. In fact, that's going to violate uniform convergence. Okay. And this is probably the easiest thing to do. Pick xn as 1 over 8n. Why? Well, plug in. So it's let's plug in here for x 1 over 8n. All right. So what happens? Well, it's 2 pi k over 8n, so it's just going to be pi k over 4n. So you'll notice that we have what's inside the sign is no larger than pi over 4. And it's between 0 and pi over 4. All right. By an easy application of the mean value theorem, sine x is bigger or equal to root 2 over 2 x for x between 0 and pi over 4. Again, it's just trivial mean value theorem, easy 511 exercise. And you get root 2 over 2, that's cosine pi over 4. All right. So this whole thing here in the numerator is going to be, well, it is small, but it's not that small. It's bigger or equal to, as I mentioned, it's bigger or equal to this whole thing here. Right? And the k in the denominator comes along for the ride. Okay. So the k's cancel. So you're just basically summing from k equals 1 to n, root 2 over 2 pi over 4n. There's no k to speak of. So the n's then cancel. So this is root 2 pi over 8. Whatever. Just call this big M. Whatever, it's certainly bigger than 0. That's for sure. Okay. All right, so let's see why this screws things up. Well, if we did have uniform convergence on 0 to a, well, certainly each fn is trivially continuous. The finite sum of these signs, right? Remember, fn, big Fn, is just k equals 1 to n sine 2 pi k x over x. That's each one of those are continuous. So the uniform limit of continuous functions is continuous, so big F has to be continuous. All right. But f of 0 is 0. We noticed that before. Big F of any integer is 0. All right, and obviously xn converges to 0. Xn was 1 over 8n. So fix n where 1, this here, big F of xn is less than m over 2. All right, and fix n where, well, this here, so let's say n is large enough, so 1 over 8n is less than little a for some positive a. You can do that trivially. If that's true, then xn is in 0 to a. So this quantity here is obviously less than or equal to, this quantity here is less than or equal to, take the sup over all x in 0 to a. And this is the infinity norm. If we have uniform convergence, we can pick n where this sup is as small as we want. Pick n large enough so that the sup is less than m over 2. And that tells us then that absolute value of fn xn is using a triangle inequality and subtract big F of xn is less than big M. Well, that's a contradiction. We computed this. It's bigger or equal to M, all right? And the contradiction is uniform convergence. We do not have uniform convergence on any of these little intervals, no matter how small little a is. All right. And so that proves it. Okay, so what we're going to do in the next lecture is go back to the integral that we had, before, and we'll look at the Dirichlet kernel and talk about general convergence of Fourier series when it converges to the function whose Fourier series we're looking at. And we'll prove initially Dini's theorem, and then we'll get to Dirichlet's theorem. Right, so we'll pick up where we left off on the where we left off at the first lecture. Okay. All right, so yeah, so maybe a slight detour these last two videos from the central theme of this course, which is a very theoretic, modern perspective and look at Fourier series and the Fourier transform. But I think this is still, still very useful. Doing a concrete example of how to prove typical Fourier series converges uniformly. Some general theorems about, some very simple general theorems about Fourier series, differentiating them, and a very concrete example of Fourier series. All right, so yeah, expect a new video maybe sometime next week. And I should say, feel free to leave comments in the videos. If you have a question, you can ask a question in the YouTube comments section. But anyway, so long, take care, and hopefully I'll see some of you soon, office hours or around campus.